In this video, we're going to talk about one of the most important uses of graphing algorithms, shortest path algorithms. So when we consider what's called a shortest path algorithm, and this is how maps work, like Google Maps and that sort of thing. The input is a weighted graph, and associated with each edge, Vi and Vj, is a cost to traverse the edge. The cost of a path, Vi through Vn, is the sum of their costs. This is called the weighted path length. The unweighted path length is simply the number of edges on the path. So, first we're going to talk about what's called the single source shortest path problem. Given a rated graph W, consisting of edges and vertices, and a single vertex X, find the shortest weighted path from X to every other vertex in W. So, let's say, what is the shortest weighted path from vertex 1 to 6? Well, vertex 1 to vertex 4 to vertex 7 to vertex 6 has a cost of 6. But the shortest unweighted path is V1 to V4. Is a cost of, from V1, V4 to V6 is a cost of 2. So, if we update our weights and arrows a little bit, the paths from V5 to V4 costs 1, but a cheaper path exists by following the loops V5 to V4, to V2 to V5. V5 to V4 is a 1. V4 to V2 would give us 4. V2 to V5 is -5. And back to V4 will be 4, or -5. It could get even cheaper by staying in the loop forever. So therefore, the shortest path is undefined. The path from V3 to V4, where we can go from V3 to V1 to V4, costs -2, and similar for V1 to 6. These are negative cost cycles, and the shortest path is therefore undefined. Negative edges aren't bad, they just make things harder. So, airline shortest path problems. Airline travel from a city to a city, transferring files from a computer to the other, and there are many others. So let's look at the unweighted case first. Given an unweighted graph G, and given vertex S as an input, find the shortest path from S to all other vertices. Given it's an unweighted graph, we are only interested in the number of edges. Let's think of this as a special case of the weighted problem, but all the weights are 1. So, only think about the length, not the path itself. If X is V3, then the shortest path from V3 to itself is 0. Now, look for all the vertices that are distance 1 away from X, meaning the adjacent ones. What vertices are adjacent to V3? Well, V6, V4, and V1. But because of directionality, we're going to drop off V4, so V1 and V6. So we can add 1. And we can continue this till all the vertices have been reached. This is known as a breadth-first search. It operates by processing all the vertices in layers. The vertices closest to the start are evaluated first, then the next layer, and so on until the most distant vertices are evaluated last. Okay? So here, we've got, we keep going until we get to the most distant vertice, and that we can, and that will give us our total weight. So how do we translate this into code? Well, let's construct a table where d of v is the distance from x and set to infinity except for x itself, which is set to 0. We set them initially to known as false. After it's visited, we'll set it to true so we don't have to revisit it. dv is a distance, and pv is a bookkeeping value. So here's the actual algorithm. For each, first we're going to set up the table. I'm going to set the distance to infinity, and known to false. We're going to have a distance for current distance equals 0 to the number of vertices for each vertex if it's not known, in other words, we haven't visited, and the distance equals the current distance. Then known equals true, and for each vertex adjacent to V, if it's not found, we then set that distance to our current distance plus 1 because we know it's one further. And then we set the path to V so we know where we came from. Pretty straightforward, not all that hard. Now, knowing what we know from the unweighted class example, we can now tackle the weighted shortest path. And PV is the last vertex to cause a change to DV. The solution is known as Dijkstra's algorithm, and it's an example of a greedy algorithm. Greedy algorithms solve a problem in stages, doing what appears to be the best thing at each stage. So for example, if we were making coins, 70, and we're making change, and we get 79 cents. 3 quarters and 4 pennies is the greedy algorithm. 87 cents would be 3 quarters, 1 dime, and 2 pennies. It minimizes the number of coins given. So, taking the previous examples, Dijkstra's algorithm, we choose a V that has the smallest DI from all unknown vertices and is adjacent to X. This path is then declared the shortest path and marked as known. The remaining step is we update DV. We didn't track DV before because we just think he gets 1. If DV equals infinity and DV equals DV plus the cost, if this new value is an improvement, we overwrite it. The algorithm decides if it's a good idea or not to use VI on the path to VJ given a known cost and a new cost. So here is the example. Pick X to be V1. The path to V1 is 0. Okay. From V1, we have a path to V2 and V4, and we choose V4, right? So V2, from V1, we can go to V2 or V4, and we choose V4. Why? Because it's less expensive. From V4, and we update the table. From V4, we have a path to V3, 5, 6, and 7. Okay, so from V4, we can get to 3, 5, 6, and 7. And we choose out of those, we're going to take V2, which is 3, as our new cheapest. Okay. From V2, we have a path to V4 and V5. We choose V5 since V4 is already known and we don't have to repeat ourselves. None of the paths are better, so we only update V5, right? From V5, we have a path to V7. None of the paths are better than V1 to V4 to V5. So we go back to selecting the smallest unvisited node, which in this case is V3. From V3, we have a path to V1 and V6. With V1, the cost is 1 plus 2 plus 4 equals 7, right? So the other way to get to V1 is 1 plus 2 plus 4 is 7, right? Well, 0 is less than it, so we're going to leave V1 alone. V6, on the other hand, is 1. Where's V6? 1 plus 2 plus 5 equals 8, which is less than 9, so we're going to update V7 now. From V7, we have a path to V6, right? With the cost of 1 plus 4 plus 1. That's 6, it's less than 8, so we're going to update it again. So, here are the shortest paths. V1 to V1 is V1. V1 to V2 is V1 to V2 straight. V1 to V3 is V1 to V4 to V3. V1 to V4 is V1 to 4. V1 to 5 is V1, V4 to V5, and so forth. So let's look at another example. VA is our starting point. Okay, we've got this set to 0 because it's self-referential. And our PV is set to 0, right? So we're going to move to VB. Okay, when we go to VB, we're going to move on from there to VC. I'm sorry, from VA to VC. And so notice here we got 3 in our table and 4 in our table. And the path is updated to show the last node that it came from, right? Now, for VD, we get to VD from VC, and we're going to update VD since our path from VA, 6 is less than 8, and VE is also a shorter path because 4 to 10 is 14, which is less than 15. So we now move to VD. VA is our starting point. We move to VD, then on to VC again. And we update the same slide, actually. And VE can't get anywhere, so we're done. So that's an overview of Dijkstra's algorithm and a good way to run through a graph to find the shortest path.